Okay, there we go. All right, so this is what we would just call a 2-to-1 multiplexer or mux. Now, all this is saying is select in a 2-to-1 is 0 or 1, right? So if it's 0, I take I0. If it's 1, I take, oops, this is I1. And then it's going to have some output, I don't know, let's just call it X. Right, so this is going to have a really simple truth table where I have I0, well, let's do this in reverse. I0, I1, select, and then X. I'm not very smart today, guys, so if I do something really dumb, call me out on it. Okay, there we go, truth table. So the only thing that matters, right? Well, the first thing that matters is what is select. So if select is 0, I care only what I0 is. So select is 0, I0, X is just going to do that. Similarly, if I have select, then I only care what I1 is. Ta-da, right? There's our truth table for a mux. And this is the simplest case, 2-to-1 mux. And if I wanted to create, I went over this last time, but it's worth rehashing. I'm going to change my notation here just to differentiate. Okay. This is now a 4-to-1 mux, notated the same way. All right. So this one, I now need to decide what the select logic is, right? So there's 4 inputs. How many selects should I have if I need 4 inputs? Yeah, so I should only need 2 select channels. Is there a simple way to wire up the selects in this point, and that point that allows me to choose A, B, C, or D? Right, because right now I have 3 selects. How do I wire them up such that I can access any of those? Well, we could do a couple of things. We could go through this painstaking process of drawing out a truth table for this whole thing, throwing that into a K-map and simplifying and see what we can come up with. Or we can recognize that I can use the first select on both of these channels, right? So select 0 is saying take A and C or B and D, and then output it to this one, and then select 1 just says take one of these outputs, right? So let's say select 0 is 0, then I put A and C on this mux, and then select 1 can choose A or C. Similarly, if I were to put 1 on select 0, this would put B or D, and then select 1 would just choose between B or B. Everyone feel comfortable with that decision tree?
So it's like the 2 select 0 that
Exactly. Yep. Yeah. The select 0 cares about the first one, and the select 1 cares about the second one. You can now cascade this into as many mux selects as you'd like. Right? I can just stick 2 of these side by side and add 1 more mux at the output, and now I have an 8-to-1 mux. Something I do want you to be aware of, just going forward, there are 2 types of muxes. There's an analog mux and a digital mux. A digital mux is most of what we care about in this course because it's digital systems. What a digital mux does is it just assigns this value to x, what I would say indirectly. So it essentially pulls the output up to 1 or down to 0, depending what the input is. But the input doesn't actually pass through here. It just uses a control signal. In an analog mux, it literally connects the input to the output. So a digital mux only passes digital signals. An analog mux can't pass either digital or analog. It's something I want you to be aware of if you, when eventually in your career you run into multiplexers. This book does something that I'm not going to torture you with making one of these, so I'm not going to go through. Oh, and I will step back and say something first. I haven't covered variable entered maps yet. The VEMs is their reference. We will cover that when I find the right time to do it. We kind of skipped over it. I don't use them very much, but I do want you to know them. So we'll come back around to that. If we have content like in this chapter 10 uses variable entered maps to derive some of these circuits, don't worry too much about that. They can be explained another way, and that's just fine. So something that you can do with muxes that is useful and interesting is you can use them to create output logic in clever ways. Let's say it that way. So let's say I have a mux. And it's going to have two selects. So this is the other way of drawing a 4-to-1 mux. Okay, all right, took a bit of drawing. So here we're using a multiplexer in order to implement a function. Now, this is almost never the easiest way to do something, but it's a method that you may come across again when you hit industry. Somebody else may like this method of designing, and so it's something to be aware of. So I have inputs of A, B, C, D, and E. And I may give you something like this in an exam and just ask you the question, what is F? Right, what is the function for F? Well, we could start, or even, I may give you a more complicated one and ask you to simplify F, right? I may say a word problem, like you get a new job at a company and you come in and see this circuit, but it's broken and they want you to design a new one and it needs to be smaller. How can we do that? Well, the first step is finding out what F is, right? And anytime we do that, a truth table or a K-map is a great way to start. I'm obviously not going to draw out this whole truth table because it would be huge. But you can start to see that the A and B choose C, D, and E, right? And this means that if I choose this channel right, it's just going to be 0. And you can start going through and say, well, if A and B are 0, it selects channel 0, right? So I have channel 0, 1, 2, 3. Well, if A and B are 0, then F just takes C. right? And this is a painstaking and awfully tedious way to do this, and I will not do something this big. So F is then just C. Now this is one place where variable entered maps are actually a little bit useful, but we don't need it, right? It's just 2 lines. If A and B are 0, it only depends on C. And then you can start filling that out. If A and B say we're 1s, what channel do I select? 3. I go in and it is now, well, F is just an output of E, D, and then you just have the NAND. Right, and everybody knows that this is NAND. It looks like a NOR, but you add the new bubbles and you have the NAND. That's something we'll talk about in the exam, actually, that some people missed. Okay, that's all I'm going to cover on muxes, really. I will probably give you some homework that kind of talks through getting equations out of a circuit. If I put one on that is creating a circuit from this, like email me and make sure I meant to do that, because it's painful and it's a terrible way to implement circuits. Like, yeah.
I've got a question. I'm just looking at the book, and there's a 2-1 voltage register that it's drawn out. I'm having a hard time like understanding. What it is.
Oh, okay, yeah.
I don't know if that's
Absolutely, yeah, if you're curious about it. 10-5, so he's asking a question. So this is just a matter of using the truth table for a mux in order to create a circuit for the mux. So and I'm not going to write all of those out. Right, but this is the truth table that chooses the one box I drew up earlier. If I want to turn this into a circuit, anytime I give you a truth table, what's a good way to turn this into a circuit? K-map, absolutely. 3 variables, so I only need one of these guys. There's K-map. I will do it like them just so it's easy to follow along. They do select and I1 and I0 here. And then they fill it in like there. Okay, I have that K-map. One good implicant, 2 good implicants. Now, the output of this one, when I'm using ones, right, is sum of products. So that means my output gate is an OR, and I have 2 AND gates with 2 turns each. Okay, so now I've got an output of an OR gate with 2 AND gates with 2 inputs each, where each one is select and I0 or select and I1, right? I feel like one of those is a bar, actually. Yes, so in order to care what I1 or I0 is, I need not select, right? So if I want I0 to matter, I need not select. If I want I1 to matter, I would need select. That's all this is saying, right? This is another way to show the mux. Now they implement this as NAND gates because we like these universal gates. Now, the nice thing about sum of product implementations is they turn into NAND gates really, really easy, right? I just add inverters here and the inputs. And if I want to undo what I just did, right? So this just broke the circuit. I can fix the circuit by re-inverting it. So I invert, de-invert. This is the exact same circuit. It's just two inverters in the middle. But it also is nice because this is a NAND gate and these are NAND gates. Now I have universal gates. Done. Make sense?
Yeah, I think I was just getting confused with the Colin Brown way of doing it. The dot L.
Yes, the book's way of the dot low. So anytime I write a signal, assume that it's right dot high. If I write S, it's S dot high. Another way of this is S dot low because of that S dot low is equal to S bar. That's just one of the identities in the book. Myself and every designer I've ever met prefers just this notation rather than the dot low. Except for on the outputs, occasionally you will actually see it be like F dot low and you'll add like an inverter here, right? So that's the thing to be aware of is, and this could happen. So you could design a circuit for F and then realize that, oh, this needs to be active low. I care about it at the output most of the time. So this is F. If I need F dot low, another way of saying that is F bar. Right. I personally avoid writing dot lows like the plague in the middle of this circuit because I would rather just write that this is not S and I naught. I could write that this is, well, bar, right? This is not S naught and I naught. The bar comes because of this. You can dot low it, but this one can be tricky because you need to be aware that the dot low applies to the whole thing. So I stick to bar. Right, because this would be, let's do this one, it's easier to say. S and I1. It would be S and I1 if not for the inversion. So you could even mentally break this out and put an inverter over here, and over here we have S dot I1, on the other side we have not S dot I1. But we need to make sure the bar is over the whole thing. And we also need to be very clear not A and not B is not equal to not A and B. So when I have something like this, I can't just split out the I1. If I want to do any factoring or multiplication or Boolean manipulation, I need to, what do I need to do to this? What's a way that I can get rid of the bar? The Morgans. So that's what I need to do if I want to start simplifying it. I can't just assume that these two are equal. Yeah, so this is NAND. What gate is this? Well, it's really like an XOR, right? This you can always A, B, Y. I guess it's an XNOR probably, right? So if I need, the only condition that this is true is if I have not A and not B. Oh, this is not XNOR. That's the A. Sorry, this one is XNOR or something, but yeah. Sorry. So that's our truth table. The only case when this is true is when I have not A and not B. Every other case is there, which is not, so if I have NAND, well, let's start with AND, right? AND is 0, 0, 0, 1. And NAND is, right? So, did I do that right? Yeah. You'll notice that Y is not NAND, right? They're not equivalent. Make sense, everyone, that truth table? Okay, let's see if I can figure out where we were at. Ah, yes, we are going to be at making a MUX and VHDL. So this is how we make a MUX in a circuit, right? Let's try and leave that up as I write some things out. So again, VHDL is a language that describes hardware. When we do this, right, we need to create, and this is going to be lots of repeat, but I hope it helps, an entity, and we're going to just call it a MUX4. They have a longer term for it, that needs ports, right? And a port is something that allows things to come in and out, just like a boat port, right? So into or out of this entity of the MUX, I'm going to have Y, which is an output of type standard logic. I'm going to have inputs of, you guys care if I just do A, B, C, D? A, B, C, D. And these are each going to be, well, they want to use integers, right? I think. No. What are we doing? INT? Ugh. Ins. Typos in this book are awful. And it's also standard logic. And then S is going to also be an input of type standard logic vector. When I create a standard logic vector, what do I have to specify?
How many bytes hold this way?
Yeah, the size of it. If I have 4 inputs, how big does my S have to be? 2. So this parentheses and semicolon ends this parentheses, and then I have 1 down to 0. And then I have an end MUX4, right? So this is creating an entity that has these ports. So it's outside of the world of the MUX, this is what it sees. So the component is drawn like so, right? It exists. The outside world doesn't know or care what's going on in there. It just knows that there's inputs and there's an output, and something happens in between. If you're ever working in Vivado and you see an error that pops up that says error, black box, something, something, the black box is because you created an entity and then didn't define what was going on inside somewhere. So the term we use is black box. To the outside world, this is a black box. Vivado doesn't like that. It wants to have it specified somewhere, right? Because in order to synthesize it, it needs to know what it is somewhere. Okay, entity. ports that see the outside world. And then we move on to architecture. I'm not going to write the whole thing out. Architecture, and you name it something like structural is, right? And then in there, we can just tell it the structure of what a mux is doing. So what is the structure of a mux? Well, it's just this, right? So I can do a couple of different things. I can say if select is 0, then f, or in this case y, is equal to I0 or whatever. Or I can write the structure of this directly in gates, where I can say something like y is, and remember we use this equal sign when we're making assignments inside of VHDL. Something like, man, I don't want to write this whole thing out. So let's start. Okay, so all I've done is take the gates and write them out explicitly. Oh, I probably need parentheses here, right? So if I don't have S1 and not S1 and not S0, so 0, 0, or, did I miss one on that one? And I0, sorry. And I guess for consistency, I can move this down here. So if any one of these is true, it's 1. If we go back to the truth table that I horrifically inconveniently erased, you'll notice that there are 4 situations in which case you'd have a 1 in that truth table. And this is just the not situation. Now this is really complicated and not a great way to do it. Especially, it can be simplified a lot more than that with if statements, right? You like if statements, if this, then that. But this is how you would assign something structurally, is we can just literally write out the specific gates, and, not, and so on and so forth. The ordering is such that ands, well, rather, nots take #1 priority, right? The next priority is ands and not. This takes place interiorly, S0 and those ones. So it nots S0 and then looks at the ands of and. So we go nots first, then ands, then ors in order of operations. Similar to multiplication, right? Because ors are plus and ands are times. The same thing as algebra with the symbols, which is why the ors need the parentheses on them to make sure that you take this or that in the correct order.
Okay.
Yeah.
The IOI one that you doesn't send it to ABO.
Yes, sorry. Okay, we'll have some homework that walks you through doing some of the structural stuff, defining gates, making sure the order of operations are correct. The mux is nice to show because the mux is relatively simple. There is another better way to write this. As I said, I don't like doing that, and you will probably never do it that way. This is another little bit of a weird way to do it, but it's much more elegant. I guess. This is another way. I'll draw a line. Y is equal to I0 when S is 0. Why do I use the quotes? Yes, because it's a standard logic vector. Now there is something that is a little bit, no, never mind, they don't do it in this one. The book does something weird later, but we'll address it then. Yeah, so when S is 0, assign it to Y to I0. When S is 1, assign it to 1. When S is 2, assign it to I2. And if it's not one of those, assign it to I3. Right? This is a nice, simple way of writing. It's really an if-then kind of statement, but condensed. We would call this a case statement. There is another, well, sorry, VHDL calls this one a conditional. Case is a more specific term in VHDL. But basically, on the condition of S, assign Y accordingly. You'll find that very useful throughout your career as a future digital designer. And I'll cover proper case statements later, because I like those more. Any questions here?
I've got a question, but it's, well, there's a question on the homework that how to do an adder, factor.
Yes.
Could you do just the first little bit of it? Maybe, I don't know.
Yeah, well, I can certainly point you in the right direction. When I want to design a circuit, what is the first thing that I would do? Yes. And then I can simply turn that truth table into a circuit and turn that circuit into VHDL. Yeah. Okay. That is a direct method of doing it. Yeah. You can also be a little bit more arbitrary, and as long as you use the correct types, an adder would just be like, I would have port, I'm going to pseudocode this. I have ports A and B and that are inputs, and I have a C that's an output, and then I just say C is equal to A plus B. Done. I just made an adder, right? This is a nice thing about VHDL, is it allows you to do this, as long as these types are correct, right? The issue is, don't get confused with assigning. In this case, this really does mean plus, right? When we're handwriting it, that means or, right? If I wanted or, I would have to write or. So be careful to not get confused with those. But the plus does work to just add A and B, as long as the types are correct. Okay. And ampersand, that's concatenation, not and. So concatenation means if A is equal to 0, 1, 1, and B is equal to 1, 0, 1, okay? Those are the terms. and I say C is equal to A and B, I end up with that.
So it's not,
Yeah, it's a concatenation operation.
it's like a programming.
And then the other one to always keep track of is that is an assignment statement where it's basically taking A and putting it into C, right? Whereas this is a comparison that will output 0 or 1, true or false. Okay. Good question. Any other? Yeah.
Actually, so what is the difference between behavioral and structural?
Behavioral is this. I am describing how I want it to behave. Structural is, this is the gates, and I built it from the ground up.
And you only need one of them in your program.
Most of the time, you will design blocks that are either structural or behavioral, and then you'll connect them together with a structural. So in the real world, what really you end up doing is most of your modules, like your adder, are going to be behavioral. And then you connect them together using structural. Very rarely will you create structural logic unless you're doing like PLCs or something that is very space constrained. If you don't have a lot of room on whatever programmable logic you have, sometimes you'll do structural because it is more size efficient to do it yourself. Because you're not at the mercy of some algorithm, right? You can just tell it to be optimal. And that's what K-maps allows us to do, is optimize for size, essentially. To answer your question, you can mix them inside of one architecture. It gets tricky to do so. I usually pick one or the other and then connect them together with structural.
Okay, it's just in our homework, there's a question, it's like, write a behavioral model for the one that holds factor, and then there's another one that's write a structural model for the
Yep, structural, behavioral. I want to make sure I leave room for the exam. Okay, we can keep this one short and simple. So there's another idea where we have demuxes and, sorry, is that later? Am I skipping ahead? Okay. Well, let's start with encoders. So encoding is an idea of taking the binary values that we have and setting to them some sort of code. Because you might want to store them in a different way. Now, one way that we kind of thought out this explicitly for encoding is that you've done like binary to 2's complement, right, is one example. That is encoding numbers a different way. Another thing to do is you're taking decimal and encoding it as binary. We need ways to store data that is friendly to the computer because they don't handle decimal, right? They work in binary or 2's complement or something else, but sometimes it's easier for us to store it in a slightly less optimal way in order to manipulate the data. So one of the weird ones that you'll encounter, I'm not a big fan of it. is called one-hot encoding. And all that's saying is that of your outputs, we're going to have say a 5-bit output here. Only one of your digits is ever going to be true. Okay, one-hot encoding. If it's 0, the first one is 1. 1, the second one is 1. And if you ever do this encoding and it starts looking for any bigger numbers, it's still only going to take this one. And if you decode from one-hot to not one-hot, it would just ignore any of the lower bits. This is like an old school. They used to use it. I still don't understand why you would ever do it, but you're going to come across it in like exercises because people who wrote textbooks love one-hot encoding. You can see how horribly inefficient it is. One of the cases I guess that it can be useful is if you're looking at specific numbers and you're sending an output that it just only wants to know, well, let's say we had a conditional, and let's call this condition on X, and you had something that is like Y equals something when X is equal to stuff, right? And then you have a whole bunch of these repeated. You could implement this logic by just looking for a one-hot encoding. It's a lot of work. I don't think I would ever do it. They talk about binary encoding in the book. Not useful. I don't know why you would ever do that. There's some history to it. So if you would like the history of why they use ridiculous binary, you can go ahead and read section 10.2. Otherwise, let's move to a useful one so that we don't waste too much of our time and talk about binary coded decimal, or BCD. You're going to encounter this a lot. Now, BCD is quite useful, but it is a little bit wasteful. So what BCD does is it says that sorry, my brain is not top notch today. Okay, here we go. If this is my decimal, I'm going to encode each of these in 4 bits, such that 0 is just 0, 0, 0, 1 is 0, 0, 0, 1, and so on and so forth, right? It's just binary. But if I wanted to write 21, instead of figuring out what all of the binary is for 21, I would write (21) is 22, 1, right? Wasteful. I don't need this many bits to represent 21, but it makes it really easy to deal with digits individually. This is helpful if you remember. So remember our problem where I was making you guys do the 7-segment display, right? Well, it's pretty easy. Each one of these can get assigned to just 4 bits. And then I can encode my decimal number in a way that fits with this 7-segment display really smoothly. Okay, so that's BCD, where they just take 4 bits and assign it to 0 through 9. The other encoding that we really, really like is called gray code. Gray code is spelled with an A and technically a capital G because it's named after some dude with the last name of Gray. You've actually encountered gray code before. Gray code is where we only change 1 bit at any given time. So whenever we make our K-maps, gray code, right? We only ever change one bit when we count up. We extend this all the way out to however many bits you have in your vector. I don't think I'll go into all the reasons we do this, but it's very optimal when doing counting operations. Because if I only have to change one bit at a time when I count through something, we consider that optimized and it's helpful. So yeah, that's gray code. You encountered it before. Now you have a name for it. The book talks about it. And I think I'm going to end there so that I can get your exams back and at least spend a little bit of time talking about it. So I'm going to start yelling out names. I just want to see hands. Brooks. Landon. Jared. Michael. Warren. Sarah. Chandler. Yeah, lots of nothings here. Okay, Jack. Jonah. All right. Cody. And Jacob. Alejandro. Pierce, I believe. Last name of, sorry. I apologize for your handwriting. Trenton? Harrison. Sean? And Zach. And is that everybody? Okay, so the exam is out of 101 points. I'm trading it like it's out of 100. There was no need to curve it. You guys did really quite well, actually. Very pleased. I did take some notes while I was grading it so we can discuss some of the issues. Okay, we got time. Number one, I think virtually everyone got it right. Number two, the only error, there was only one type of error I think that I saw, that I recall, and it's that some people assign 2 to the least significant bit. So if you had 1, 0, 1, you're assigning this a value of 2 rather than 0 or 1. And that just put you 1 digit off. So if you end with a 1, it needs to be odd. Yeah.
That first question for problem B.
Yeah.
What was the answer to that?
Did I mark you down at all? Or
No.
So that one, I didn't even write it down. I basically didn't mark it down because this is my bad. It wasn't possible to do that conversion because it took more than 8 bits.
Right.
And I breezed through writing this too quickly and I screwed that up. So almost all of you got it, actually. Most of you wrote not possible. So good job, guys. But I didn't mark down because I'm the idiot and didn't do that right.
Yeah.
Yes. Yeah. 3, I literally not sure anybody missed it.
Oh,
6, the only, this one was hit or miss. So the trick that I like to use when I'm subtracting numbers, I kept this fairly simple for the subtraction. I didn't like do add or subtract, that gets confusing. Let me write up this first problem, and I think that will explain the issue for everyone. Many of you will notice I'm pretty generous with the partial credit. So as long as you gave a good faith effort to, you should get points for things. So I specified that these are 8-bit 2's complement numbers, right? We know that these are negative, right? Because there are ones in this ones place. So there are a couple ways that you can handle this subtraction, and all of them are okay. One of the ones that I liked, actually, there was someone that went through all of the math and it ended up being wrong, and then they just converted this to binary, to decimal, that to decimal, and then did that, and then converted it back. That's totally fine. If you get lost, right, you can just turn these into decimal numbers, do the subtraction, and move on. Takes a little bit of effort, but it's not wrong. The other thing that you can do, and this is the one that I like, is you can recognize that this and this are positive numbers. The only negative part is this column. So let's treat them like we're just adding, right? So 1 and 1, 1, oh sorry, 0. 1, 1 and 1, right, is 1 with a carry. 1 and 1 is a 0 with a carry. That's a 1, carry's gone. 1 and 1 is a 0 with a carry. 1 and 1 is a 0 with a carry. 1 and 1 is a 0 with a carry. Okay. Now I have a positive 1 at this location, a negative and a negative. Right, so I'm adding 2 negatives, but one of this positive 1 can cancel out completely one of these negatives, right? Because whatever this digit is equal to the carry value of the previous one. So this 1 cancels this 1, and I end up with just 1 there. If I didn't have this carry, then I would have to borrow and it would be overflow, right? So then I would have -1, -1, and have to start, well, I might have to start worrying about it anyways. Might be okay. Nope, you have to borrow. So that's your issue, is that if you have 1 there, it adds up, not, and these 2 subtract. B, everyone got. The second one, or C then had overflow, which was, so the mistake was there, is that these were 2 positive numbers that ended up with a 1 in the most significant bit. So some of you thought it didn't have overflow because it only had 8 bits. But what you ended up with is adding 2 positive numbers together and then you got a negative. K-maps, mixed results, generally positive here actually, pretty good. Common issues, C, there's a group of 8 along the top and then along the bottom that you could snag, and then a group of 4 in the top right. So the B was mostly correct, A was almost all correct. Yeah, you guys did really good with this one, actually, the K-maps. A couple of you don't know K-maps. If you did poorly on the K-maps, I strongly recommend coming to office hours and talking about them. These 4 variable K-maps are going to be important, and eventually we will get to the variable entered maps and do 5 and 6 variable stuff. But you want to start with a strong foundation at 4. So if you did poorly on this, make time for office hours with me, either via Zoom or in person, or at least look online. There are tons of resources for K-maps, but this is an important thing to know for all of your digital courses. 6, most of you got right. Again, if any issue really came from filling in the K-map wrong. 7. So here we're supposed to name the identity. If you couldn't name it, but you wrote it out, I give you partial credit. So the first one, you can make an argument that it's either complementary or logic adjacency. The second one is just a property 1 or absorption. Either one of those you can make a case for. The third one is just De Morgan's. Fourth one is distributive. And the last one is complementary. Yeah.
So okay, it says identity, property, or theorem, in the book it also has pool, you make a big, form that you use to write the word.
No. I didn't need you to write if it was what the type of it was.
Okay.
I just needed you to write what the name of it was.
Yeah.
So if it was the complementary theorem versus identity, there's not going to be a markdown. It's just, did you write the right one? 8 was a really mixed results one, which is okay. The first one is a NOR gate. And that's because if you look at it, if either A or B is true, it has to get pulled to 0, right? Because those switches turn on and pulls it to 0. The one thing you can always count on is ground will always win. There is no supply that is going to outsupply ground. In general, in circuits until you get to like high power stuff. But just for most of your circuits, assume that nothing is going to beat out ground. And so if A or B connects Y, the output to ground, you have your truth table right there, and it's a NOR gate. Similarly, the NAND gate is as long as you have not A or not B, it gets pulled to supply, and you need A and B in order to pull it to ground, right? And so some of you wrote AND gate rather than NAND. I'm a big proponent of writing out truth tables for things when you're not quite sure. C, now this was a fun one. This is one of so what I like to do is create lots of questions that most of you will get right, a couple of questions that a good chunk will get right, and a couple that a lot will miss. This is one of those harder, trickier questions. I recommend just going through and writing out the truth table on this one if you don't see it, but it's just an XOR gate. Because it's still only 2 inputs. You have A and B. It's just some of them are inverted. And then in order to get a value, you have to have A or B, but not both. Therefore, XOR. 9, I'm not going to go through. Some of you missed this one. If you missed this one, you really need to review number 9. It's just standard logic gates. True or false? The first one, I was just hammering home that, right, I wrote this up before, the same idea. Those are not equivalent. This is an error that I see at both this class and my 3610 class. Don't make this mistake. There will be more of those. The gate is an inverter.
I have a question on that one. So on A, 10A,
Yeah.
it's A, B, or A not, B not, or B not.
Yep. So if you have this, this is true.
Oh.
This is not true.
Oh.
Okay, C, considering that programmers and designers often truncate leading zeros, the following 8-bit 2's complement number is negative. So what this means is a lot of times if I say, I'm going to write up an 8-bit number, I don't write all 8 bits, right? I truncate the zeros. This only has 7 zeros, therefore it's a positive number. D was a little bit tricky. Just checking if you remember the technologies. It was asking about hardware technologies. TCP is not a hardware technology. It's a software protocol.
Yeah, we're not sure.
Yeah. No, a lot of you were really suspicious of that one, but then didn't. I liked the awareness, but I didn't like the follow through. Let's say that one. 11. You guys did some really creative things on this one, but overall it was really good. I'm the biggest fan of when you're trying to make universal gates. So right, I have an OR gate and an AND gate of doing what I call the bubble pushing, where I just create 2 bubbles and push one all the way to the other side. Some of you did some really complicated things that I didn't quite follow, and I had to write out and figure out what you did. The only tricky one on that really was that you have the C branch that goes into an OR gate and then comes here. A lot of you missed that it needs an inverter if the AND gate down, or OR gate, whatever it was, gets a bubble. I need to then do something with a bubble, right? I need to re-invert it. So that was the only real common mistake I think I saw on that one. And part A was good. I know one or two of you probably have a really long explanation of why you missed B, or at least missed some points on B. I don't think anyone missed all of them. If you have questions on that, you can talk to me. There were two of you that I had like go out and have to start drawing some serious equations to puzzle out what you did because it was really weird. But okay, LED. I would say more than half of you got this right. And those that you missed it at least got the right idea, right? So I'm just asking, when does this LED turn on? If this is VCC over here, then I go from 5 volts to 5 volts and nothing happens, right? So the circuit doesn't do anything unless there's a difference in voltage. So when the signal in is equal to 0, then current can flow. If it's high, no current flows. So part A is low because it needs a pole to the ground to turn it on. Part B is 0. And then part C is just the voltage drop according to Ohm's law, where I'm going to go from 5 and then I lose out some voltage from the diode, which I specified at 2 volts. So it's just 5 minus 2 over the resistor. I think I gave you guys the 1 of the 2 points as long as you got Ohm's law written down correctly, essentially. 13 was excellent. Good job. You guys learned from the homework. That was just 15 millivolts times 18. The only mistake that really happened is you multiplied by 18%, so 0.18. But it's 15 millivolts per percent, not per 100%, if that makes sense. 14. This could have been really tricky. It was on the practice exam. As a result, on A, most of you did it right. I think there was like 1 or 2 that missed it. But that went overall well. B, ironically, I actually screwed this one up when I started grading, so some of you might have some weird scratches, because I did what most of you did, if you missed it. Most of you got this right, actually. But if you missed it, it was because you filled in the KMAP wrong. And some of you did a weird thing where you changed them from D0 to D3 to A, B, C, and D, and then never converted back. And it was unclear in a couple of cases what it was unclear if A was D3 or D0. And part C, I think hopefully by the end of today, right, it's just more of this, just push some bubbles around. And this one's really simple, part C, because it's only 2 levels. You have an AND gate, an OR gate at the output with AND gates behind it, and then you just turn both of them into NAND gates and you're done. Do we have any questions on the exam? We have 7 minutes or so that I can answer through. I tried to mark up and be clear what you missed on the.
On that last one, for the inputs, instead of a bubble, would you put an invert?
Yes.
Yeah.
Yeah, because the issue is that this implies that it's part of the gate, whereas this is clearly an AND gate with an inverted input. right? When we start fixing bubbles to things, we start saying, well, this is part of the game.
Yeah.
Hopefully I didn't mark it down too much if you did this or the other one. Yeah. Oh, no, it was, no, yours ended up being correct, but when I was thinking through, I was having to follow the process. And it looked wrong at first, but it ended up being okay. Yeah, so if you see like okay somewhere, a lot of times it's because I had like an X or something, and then I turned the X and they went okay or something, because I realized that my first instinct was that's not right, but then I realized you did something different. And the process is not what I'm really grading on you. Well, partial credit for doing a good process, partial credit if you get the right answer, right? It's helpful if I know what you've done. Yeah, the only times that you didn't get partial credit really is if it was really, really wrong, or if I just had no idea what you were attempting to do, or you didn't show any work. Other questions? Okay, good job, guys. I'm quite happy. I will try and keep moving forward grading the homework so you have a better idea. The homeworks, I don't know if I mentioned this. I think I did. I'm going to switch to kind of grading. Basically, I'm going to assign quarters to every however many points they're worth, and you'll get half of them for trying, a third point if you did a good effort, and a full credit if you got the right answer. So just a quick elaboration. So say something was 6 points and you got the wrong answer, but you had a good faith effort. So then I would just take 6 times 3/4. Right, so you get the wrong answer, so it's 3 out of 4. That's how I'm just going to grade the homeworks to speed it up so I can actually get your homework traded and you can know what you're doing. As long as you do well on the homeworks and the labs, it should average out with your tests to do pretty well. But overall, I'm happy with how you guys did.
So for the lab today,
We're going to be doing VHDL.
so if I don't have it on my computer,
We'll be in that lab. They're all installed on that lab.
okay.
And I will start off the lab, and this is for people watching the video if you're still around. I will make a test bench video. I said I would do that. I didn't get around to it. I will start off the lab with an explanation of test benches. Actually, I can do a 3-minute explanation of test benches. They're really easy.
So for the homework, how you said there's something online, like some online resource that you can use to type up code,
Oh, yes, there is.
or can I just use Notepad++?
You can also use Notepad++.
But can I create a test bench in Notepad++?
You can create it, but you can't run it.
Oh.
So you'll need a simulation tool, which is what this other thing is. It's called EDA Playground. I haven't really used it very much, but I will introduce it. So the general idea of a test bench is, man, I'll just create a video. It's going to be way easier than trying to go through this. But a test bench is just a way of taking the device that you created called a unit under test, UUT, and applying inputs to it and just watching what happens to the outputs. And I'll create a video that shows how to do that, because it's not very difficult. It's way easier than creating a device. But a lot of you will end up actually making test benches as your first jobs. Anyways, other questions? Cool. I'll see you guys for lab.